Okay, let's summarize and see what the key ideas are that we have extracted from these three simple combinatorial experiments. So, here's a summary: chance and commonplace settings where sampling is from finite sets, and in such settings the idea of balls and urns gives us a potent metaphor. So, we're beginning with a combinatorial setting. Well, what is a combinatorial setting? Implicit here is the idea that all chances are equally likely, all outcomes are equally likely. This is the heart of random sampling. We have a chance experiment which has outcomes which range across a finite collection of possible outcomes. This finite number could be very large, but it is bounded. It is a finite set, sometimes called a universal set, and in this context invariably represented by the uppercase Greek letter omega. So uppercase omega always represents for us the space of all possibilities for the chance experiment at hand. It is a set or collection of all possible conceivable outcomes of the experiment. Now, what is important here is not that we've actually done the experiment, but it is important that we be able to conceive of doing it. And this is the heart of the modeling: a conceptual experiment, a thought experiment, or in the German, a Gedanken experiment. And omega then represents all possible conceivable outcomes in such a setting. The next step is to identify events of interest. And an event is always represented by an aggregate or a sub-collection of the possible outcomes in the experiment. From a notational point of view, it will be good to give events simple, small, compact names. And by reasons of tradition, we will call events by uppercase letters at the low end of the alphabet. So, for example, uppercase A or B or C or D could all represent events of interest in a particular chance setting. And finally, we're interested in a probability measure. Our probability measure then has to ascribe a notion of chance. Very vaguely, we'll keep in mind that the idea of chance means that if we do the experiment many, many times, then a certain event occurs a certain fraction of the time. This is the idea we want to ascribe to chance. Of course, we'll want to formalize this. Some colloquial notation is useful in describing these settings. So, for example, colloquially, we will say that an outcome is favorable for an event if it is in the aggregate of outcomes which comprises that event. And so colloquially, we'll imagine that if we do an experiment and an outcome in an event occurs, an outcome favorable for the event occurs, then we will say that event occurs. And so now our idea of chance in a combinatorial setting is very clear. The chance or the probability we want to ascribe an event in notation, a bold font uppercase P for probability, with an argument, the argument being the event of interest to us, a collection of outcomes. In a combinatorial setting where the outcomes are equally likely, the probability of the event is very simply the number of outcomes which are favorable to the event at hand. In other words, the size of that set divided by the total number of possibilities. And in notation, we can capture all of this very cleanly and simply. P of A, the probability of the event A in words, is the number of outcomes favorable for A divided by the total number of possible outcomes. Even more compactly, we can say this is the cardinality of A divided by the cardinality of omega. Card or cardinality represents the size of the underlying set. Now this already gives us a starting point. Chance experiments are characterized at this level by outcomes, events, and probability measure. Our setting so far has considered a simplistic view where we have a finite number of possible outcomes and everything is equally likely. In other words, we have a combinatorial setting. Our next step is to relax these constraints, move away from the straitjacket. What if chances are not equally likely? What if the die is loaded? What if the coin is unfair? And move one step further beyond that and at least envisage settings where you have chance experiments where the number of possible outcomes is not finite anymore. The number of possible outcomes is infinite. Now, of course, the moment you have an infinite number of outcomes, they cannot all become equally likely. How should one handle this? Is there any worth in handling this? And so, we want to build a theory which allows us to expand into real-life settings, into problems of heft and importance. And so we'll want to consider this next. Now, before we do this, I will want to take a detour through a tableau where the ball and urn models we are looking at, which implicitly kept in mind distinguished balls and distinguished urns, are relaxed. What if instead of having two distinguished balls, a red die and a white die, what if we had two balls which were indistinguishable? What now? How does the game change? I will illustrate this in a setting of interest in its own right, in the setting of statistical mechanics, and in the turmoil of the early part of the 20th century when quantum mechanics was taking center stage. And the story is interesting in its own right and gives us actually results which seem to fit real models of real particles very, very well. This is a dangerous bend section and you should glance at it advisedly. If you're interested, if you're curious, by all means look at the next tableau. If not, you can jump ahead to the following tableau where we relax the idea of chance in combinatorial settings to take in the idea of chance where the probabilities are unequal and the space is possibly infinite.